Okay, your grade A mathematics teacher here, Beatrice. Today we are learning about Bayes' theorem. Bayes' theorem. Now you remember we saying that Bayes' theorem actually is related to the total probability rule. So we start by recalling. We recall total probability rule. Start by recalling total probability rule. You remember we saying that we consider two events, A1 and A2, which are mutually exclusive and also exhaustive, and another event B. So that we're saying that B, this set B, is given by A1 intersection B plus A2 intersection B. We indeed introduce probabilities, and we say probability of B is probability of A1 intersection B plus probability of A2 intersection B. And having done that, we introduce conditional probability. We introduce conditional probability, and we say probability of B is probability of A1 times probability of B given A1 plus probability of A2 times probability of B given A2. So once we have that, we say this is total probability rule. Total probability rule on B given two mutually exclusive, and exhaustive events A1 and A2. That is total probability rule. So when we are writing Bayes' theorem, we look at the total probability rule, and we see that we have probability of A1, B given A1. We have probability of B given A2. So we say, suppose we need to get probability of A1 given B or probability of A2 given B. What would we do? So we'll just work with one of them, that is probability of A1 given B. So we say probability of A1 given B is probability of A1 intersection B over probability of B. And you remember that we usually write the intersections in terms of conditional probabilities. So we can write the numerator as probability of A1 times probability of B given A1. All this divided by B. So what I would like you to note here is that this probability of B is what we called the total probability. It is the total probability. So if we move up to where we wrote it, we say probability of B is probability of A1 times probability of B given A1 plus it is here. So we can actually come and rewrite probability of B that way. So we say probability of A1 given B is probability of A1 times probability of B given A1 all that divide by probability of B, which is a total probability. So it is over probability of A1 times probability of B given times probability of B given A1 plus probability of A2 times probability of B given A2 plus probability of AN times probability of B given AN. So what we have now here, what we have there is what we have here, this one, is what we call Bayes' theorem. So this is Bayes' theorem, but it's Bayes' theorem which is not in general yet, because we are just considering two mutually exclusive and exhaustive events, A1 and A2, and another event B. So suppose we want to write Bayes' theorem in general. So we say in general, when we have A1, A2, all the way to AN as mutually exclusive and exhaustive, is mutually exclusive and exhaustive, is mutually exclusive and exhaustive events, and B is another event. B is another event, of course, that cuts across them all. We usually write Bayes' theorem in general as this way. We would like just to go back to the Bayes' theorem that we have written here. So in this case, in general, we are not going to have A1 given B and A1 times probability of A1 given B. So what we are going to have, every place where we have A1, we write a general AR. So allow me to write it down here. So we are going to write it down here this way. We are going to say, let me get enough space here to write. So we write it as probability of AR given B is equal to probability of AR times probability of B given AR, all divided by, the denominator remains the total probability. So it is probability of A1 times probability of B given A1 plus probability of A2 times probability of B given A2 plus all the way to probability of AN times probability of B given AN. So we write AR because it could be A1 given B, it could be A2 given B, it could be A10 given B, depending on how many mutually exclusive and exhaustive events we are dealing with. Depends on the number of mutually exclusive and exhaustive events that we are dealing with. So we would like to look at an example. So we write this example. We say in a factory manufacturing bolts, machines A, B, and C produce 25%, 35%, and 40% of the total production, production. Okay, so we continue and say, out of all the produced bolts, 5%, 4%, and 2% of bolts produced by A, B, and C respectively are defective. They are defective. So we ask ourselves, we say this: a bolt is selected at random. A bolt is selected at random and found to be defective. It is found to be defective. What is the probability? What is the probability that it is manufactured? It is manufactured by 1, A, 2, B, this is simply A, 2B, and 3C. So we are going to solve that problem using the total probability rule and Bayes theorem. So under the solution, first of all, we illustrate the problem in diagram. So in mathematics, if there's anything that you can illustrate in diagram, you do exactly that. We have machines A, machines B, and machine C. A produces 25% of the production, B 35%, C 40%. And out of all the bolts produced, we have some that are defective. And we know that those produced by A, 5% are defective, so 0.05. 0.04 from B are defective, 0.02 from C are defective. So first of all, we ask ourselves, what is the probability of getting a defective bolt? It is probability of getting a bolt from A, which is defective, plus probability of getting a bolt from B, which is defective, plus probability of getting a bolt from C, and that bolt is defective. And so this introducing conditional probability, we say it's probability of A times probability of defective given it's from A plus probability of getting a bolt from B times probability that a bolt is defective given it's manufactured by B, then probability of getting a bolt from C times probability that a bolt is defective given that it's from C. So this is 0.25, this is 0.05. We add that to 0.35 times 0.04, and we add that to 0.4 times 0.02. So when you work out that, you're going to find that the probability of getting a defective bolt is actually 0.0345. It is 0.0345. So we come and now ask ourselves that a bolt is selected at random and found to be defective. So we want probability that is manufactured by A given that it's already found to be defective. So this is probability of A intersection D over probability of D, which is probability of A times probability of D given A. All this divided by probability of D, which is a conditional probability. So probability of getting a bolt from A is 0.25. Probability that it's defective when it's from A is 0.05. And the total probability is 0.0345. So that if you work out that to 3 decimal places, you get 0.362. So we move on and say probability that a bolt is manufactured by machine B, given that it's defective, is probability of B and defective over probability of getting a defective bolt. So it's probability of B times probability of defective given B over probability of defective. So the probability of getting a bolt from machine B is 0.35. The probability that it's defective is 0.04. And the total probability is 0.0345. And if you work out that, you get 0.406. Okay, so we go to the last bit. We have probability that a bolt is from C, given that it's already defective, is probability of C and defective over probability of defective, which is probability of C times probability of defective given C over probability of defective, which is the probability of getting a bolt from C is 0.4. Probability that it's defective is 0.02. And the probability that the total probability is 0.0345. So when you work out that, you get 0.232. Get 0.032. You could actually now add up. You could add up the probabilities. The probability that a bolt is defective, given that it's from A, is 0.362. The other one is 0.406. And the other one is 0.232. So if you add up probability that a bolt is from A, given that it's defective, plus probability that a bolt is from B, given it's defective, plus probability that a bolt is from C, given that it's defective, you put that together, you get 1. So that is how we work with Bayes' theorem to solve problems. So that ends our lesson for the day. Thank you.